Okay, in this portion of the chapter, we're going to learn about pH. I am on slide number 6 of PowerPoint 4B. pH is a way that we indicate how acidic or basic a particular solution is. And first I'll mathematically define pH for you. The pH happens to be the minus log of the proton concentration. So you may not be real familiar with logs. You can use this in your calculator. You better understand or at least know where the log function is and how to use it on your calculator. I want to give you a little feel for what we're talking about when we talk about pH. So let me give you a couple solutions here. And you can follow along. There's a larger list on PowerPoint slide number 6. But I'm going to have some pHs listed here. We'll just do a pH of 0. Let's start with 1. 1, we'll do a pH of 7, and we'll do a pH of 13. It turns out we can also define pOH, which is going to be the minus log of the hydroxide concentration. And it's interesting that if we have a solution with a pH of 1, its pOH is 13. And it turns out that the sum of these, the pH plus the pOH, is always 14. So if something has a pH of 7, its pOH is going to be 7, because this sum is going to need to be 14. And if something has a pH of 13, its pOH will be 1. Again, because the sum of these need to be 14. And if you look into your columns on PowerPoint slide number 6, you'll see this is the case. For every pH and pOH, you add them together, you get 14. Now, what I'd like to do is I'd like to show you what the proton concentration and the hydroxide ion concentration are for these particular values of pH. It turns out that if I have a pH of 1, the H plus concentration is 1 times 10 to the first molar. If the pH is 7, then the H plus concentration is 1 times 10 to the negative 7 molar. And can you guess this one? If my pH is 13, if my pH is 13, the H plus concentration is going to be 1 times 10 to the minus 13. Similarly, for these, a hydroxide concentration of 1 times 10 to the negative 13 molar is going to be a pOH of 13. A hydroxide ion concentration of 1 times 10 to the negative 7 is going to be a pOH of 7. And a hydroxide ion concentration of 1 times 10 to the negative 1 molar is going to have a pOH of 1. And I want you to recognize that even though this number is smaller than this one, this concentration is much, much, much bigger than this concentration here. It's actually 10 to the 12th. 10 times 10 times 10 times 10, 12 times more concentrated than this. And that, you remember, 0.1, that's equal to 1 times 10 to the negative 1. This, oh boy, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Let's see if I did that right. Yeah? This concentration corresponds to this written out in decimal form. So we see that 1 times 10 to the negative 13, that concentration is much, much, much less than a concentration of 0.1. And this is what you want to remember when you're dealing with pH and with pOH. Now, in solutions of various pH and pOH, we should recognize that in the case where my pH is 1, my H plus concentration, my proton concentration, is much greater than my hydroxide ion concentration. And if you remember that H plus indicates acid and hydroxide indicates base, we see that if we have a pH of 1, the acid concentration is going to be more than the base concentration, and therefore if you have a pH of 1, you've got an acidic solution. And this will be true all the way up until you hit pH 7. I'll just show you here at pH 6. At pH 6, my H plus concentration is going to be 1 times 10 to the negative 6, which will be greater than my hydroxide concentration. This plus this has got to be 14, which is 1 times 10 to the negative 8. And so at a pH of 6, it is still the case that my proton concentration is greater than my hydroxide concentration. So anywhere below 7, we have an acidic solution. And you should also notice the further you get away from 7, the further you get below 7, the more acid concentration you have. And that's the way the pH scale works. At pH 7, you're neutral. You see that? Your proton concentration and your hydroxide ion concentration are equal to one another. So at a pH of 7, you're in a neutral solution. And as soon as you get above pH 7, let's say we get to pH 8. At pH 8, what's your POH going to be? They got to add up to 14. That's going to be 6. And in this case, your H plus will be 1 times 10 to the negative 8, which will be less than your hydroxide ion concentration, which is 1 times 10 to the negative 6. So in this case, if your pH is above 7, then you're in a basic solution. And the further above 7 you get, the more basic it gets. Once again, we'll throw in here a pH of 13, 1 times 10 to the negative 13, which is much, much less than 1 times 10 to the negative 1 molar. So as you get higher and higher and higher above the pH of 7, the more basic you get. As you approach 7, the more neutral you get on either end. So there are a few mathematical relationships that we can write. I've already written 2 that we can write between the pH and the H plus concentration, the POH and the hydroxide ion concentration. There's this. pH is negative log of the H plus concentration. We can also use the following, the H plus concentration, that's equal to 10 to the power of the negative pH. This ends up being a useful equation. We also can write POH is going to be equal to the minus log of the hydroxide ion concentration. And similarly, we can write the hydroxide ion concentration is 10 to the minus POH. And it always turns out that pH plus POH is going to be equal to 14. These are all very useful relationships when you're doing problems that deal with pH. I'm going to show you how one can go from here to here. Some people find this derivation to be useful. It helps you remember a lot more of these rules. So we'll show you that. So let's see, if I have pH is the minus log of the H plus concentration, the first thing I'm going to do is I'm going to multiply both sides of this by -1. That makes this positive, and that makes this negative. So I have negative pH is the log of the H plus concentration. Now I want to get H plus equals something, so I got to get rid of this log function. And what we do in algebra, when we want to cancel a particular function, we take the inverse of that function. And it turns out that the inverse function of the log is 10 to the power of x. So let's see, 10 to the x, like this. So it would work like this. Let's say I have, I don't know, x is 2. Okay? And if I take the log of 10 squared, these cancel. 10 to the power of cancels the log. And so we can sort of cancel those two out and get 2 as our answer. Another way of looking at this is I can take, this, like here, if I have 10 to the power of log 2, once again, these cancel, they're inverse functions. So 10 to the power of cancels the log, leaving just 2. So, if I want to get rid of this log function, I'll take 10 to the power of this whole side of the equation. And by doing that, that cancels. But in algebra we know whatever we do to one side of an equation, we have to do the same thing to the other. So, 10 to the power of the negative pH. And there we have it, right? 10 to the power of the negative pH is the proton concentration. And that shows you how you can go from here to here in particular problems. So let's say, I just want to show you how you can do some of these problems very quickly without a calculator to sort of get estimates. So let's say I have a solution that has a proton concentration equal to 2.7 times 10 to the negative fifth molar. Well, I can look at that and I can guess the pH is going to be about 5 right away. pH, it's not going to be exact, it's going to be roughly 5. Now how did I know that so quickly? Well, you just look at the power of 10. You just take the negative of the power of 10. I'm looking for H plus. I'm looking for H plus concentration. And the H plus concentration is going to be the negative log of this. And we're just dealing with powers of 10 when we're dealing with logs, essentially. And so I'm going to focus it on this, and I just take the positive of whatever this is. It's that simple. Now I can actually do it in my calculator here, which you should know how to do this. But I like to, before I do a calculation with pH, I like to in my head say, yeah, it's going to be roughly 5, so that after I get done with the calculation, I know if it makes sense or not. So I'm just going to punch in 2.7 times 10 to the negative fifth, and then I'm going to hit the log button, and I get negative 4.56, of course, but the pH is the negative log of that. So let's remember here that pH is the minus log of the H plus concentration, which in this particular case is going to be the minus log of 2.7 times 10 to the negative fifth. And when I run this in my calculator, I get 4.57, which is pretty close to 5. Again, you can tell by looking at the powers of 10 that you're dealing with. Usually what you'll see in the text, I'll give you a tough one here. You'll see something like this in the text. Solution has a pOH equal to 12.7, and then they'll ask you, what is the concentration of H plus? This is a pretty difficult question where you're going to have to recognize that I'm going to have to change hydroxide in some fashion to my H plus concentration. And there's a lot of ways to get there. Now, I'm just going to show you one particular way to get there. I happen to know that the hydroxide ion concentration, actually it's going to be easier to do this. It's going to be easier to remember that pH plus pOH is 14. And so I'll just simply plug in 12.7 for my pOH. So my pH plus 12.7, that should be 14.0. I'll subtract 12.7 from both sides. What's that, 3.3? pH is, no, 1.3. What am I talking about? Yep, looks like 1.3. So my pH, therefore, will be 1.3. And that means my H plus concentration, very simply, is 10 to the minus 1.3 molar. Now, of course, we like to see this written a little differently, so I'm going to plug this into my calculator as follows. I'm going to take 1.3, I'm going to make it negative, and I'm going to take 10 to the power of that. And I get my H plus concentration is 0.050 molar H plus.